Hello viewers, welcome to my YouTube channel Math with Dr. Saeed. This is our third lecture in the video lecture series on fractional calculus. In the second lecture we studied about Grunwald Letnikov Fractional Derivative which we constructed in the last time, and we saw that definition as it is shown here is quite complicated. We need to convert this definition into some useful format. Today we will go through this definition for different values of alpha and drive some pattern which is easy to use and applicable to find fractional integral of some elementary functions. So this is alpha order derivative of a function equal limit n tends to infinity 1 over h, where h is x minus a over n, a is constant less than x, summation from j0 to n negative 1 to the power j alpha cj f of x minus jh, h is defined here. So this is the order of differential fractional derivative. First we need to change it to negative alpha. Negative alpha will represent fractional integral, as we know that integration is nothing just anti-differentiation. So if we multiply negative to the order of differentiation, it will just convert to integration. So when we change the sign of alpha, since in this expression they are here alpha and here alpha, this is alpha can be settled very easily, but here since it is combination symbol alpha cj, we need to figure out what it becomes if we put alpha to negative alpha. So since we know that alpha cj by definition it is alpha factorial over j factorial and alpha minus j factorial. This is the definition of combination symbol. Alpha factorial, which can be written as alpha into alpha minus 1 into alpha minus 2 so on, and if we stop it to some integer j, because j is always less than or equal to alpha, so if I stop it alpha minus j factorial, and if one previous term will be written as alpha minus j minus 1, so I just expanded alpha factorial, and in the denominator everything will remain as it is, alpha minus j factorial. So in this expansion this cancels out this one, and the remaining can be written as, and now if I just switch alpha to negative alpha, alpha to negative alpha, so this becomes negative alpha cj equals negative alpha minus 1 and so on, negative alpha minus j and minus minus plus plus 1, and in the denominator j factorial. Okay, this is product of factors. How many factors? If before it we need to we can see that negative 1 is in the every factor, so take it common. Negative 1 is factored out to the power equal number of factors, becomes, if you take negative outside, becomes alpha plus 1 so on, alpha plus j minus 1, and now we can count how many factors they are. If starting from here it is alpha, we can say alpha minus 0, this is alpha plus 1 so on till j minus 1. So starting from 0 and 1 and so on and j minus 1, so total they are, since they are starting from 0, they are j plus 1 factors. So we took j factored negative 1 out common, so this means negative 1 to the power j, and in the denominator j factorial will remain as it is. Okay, now this becomes minus 1 to the power j, and now if I switch the order of multiplication, instead writing up from this side I can write from that side. This becomes alpha plus j minus 1 and then so on till alpha plus 1 into alpha whole over j factorial. And now if I multiply and divide this by alpha minus 1 factorial and alpha minus 1 factorial, since alpha minus 1 completes its previous terms to 3 to 1 because it's factorial, so this is the complete sequence from 1 to till alpha plus j minus 1. So this whole expression will become alpha plus j minus 1 factorial. So this equal to minus 1 to the power j alpha plus j minus 1 factorial, and in the denominator j factorial alpha minus 1 factorial. And again in the gamma function symbol, gamma of n equal to n minus 1 factorial. Using this notation, this last expression will take the form minus 1 to the power j gamma of alpha plus j over j factorial gamma of alpha. Okay, this is the value of negative alpha Cj. Okay, now I will in this expression switch alpha to negative alpha, and then I will use this expression here. So this will take the form so plugging alpha to negative alpha, this becomes f of negative alpha x this one. And now plugging the value of minus alpha Cj, this becomes limit n tends to infinity h to the power alpha. I just solve this power, making it positive, just turn out inside the fraction, and then summation j from 0 to n minus 1 to the power j, and then this has the form minus 1 to the power j gamma of alpha plus j over j factorial gamma of alpha f of x minus j h. Okay, here negative 1 to the power j and again negative 1 to the power j, it becomes negative 1 to the power 2j. J is an integer, 2j will always return an even number, so negative 1 to the power even number will always a positive number, so they will cancel out. So what we are left with, limit n tends to infinity h to the power alpha summation j0 to n gamma of alpha plus j over j factorial gamma of alpha f of x minus jh. Okay, so we have arrived at this point. We have converted alpha to negative alpha and change from fractional derivative to fractional integral, and now we have to set the values of alpha and see what form it takes. So for example, if I take alpha equal to 1, this becomes I1 of f limit n tends to infinity h to the power 1 summation j0 to n gamma of 1 plus j over j factorial gamma of 1 f of x minus jh. So I just replace alpha by 1. Gamma 1 plus j, again by the definition of gamma 1 plus j for j factor j integer is just j factorial. So this is j factorial, this is j factorial, they cancels out. Gamma 1 is 0 factorial, which is 1, so this whole factor is 1. So it becomes limit n tends to infinity summation j0 to n h time f of x minus jh. This is simpler form, and this is a famous form. If you remember, this is the definition of Riemann integral. To know more about Riemann integral, just see here. Okay, so we have a function y equal f of x. It has a graph. We take a point A, this is point A, to point B. We want to find area under this graph y equal f of x from the point x is equal to A to x is equal to B. If I divide this region into a number of rectangles with same width h, this is first rectangle h, second rectangle again width h, third and so on, nth rectangle, and if this is the point x, my starting point, the height of this rectangle would be f of x. Second point is just x plus h and its height would be f of x plus h. This is the third point, x plus 2h, then x plus 3h, so on, x plus n minus 1h, and the last point x plus nh, whose height will be x plus nh, where h is b minus a over n. B minus a is, this is the interval a to b, so b minus a is the length of interval over n, which is number of rectangles, so this is the width of each rectangle. So area becomes, this whole area is basically the area of triangles with this error, which can be reduced if you take limit. So the area of triangles, first triangle, second triangle, the area of first triangle is the width into height. This is the formula of finding area of triangle. Rectangle, first length into width h time f of x, and the second rectangle h time next height, which is f of x plus h, and this is the area of third rectangle, and so on to the last rectangle. Since h is same for each rectangle, it can be taken out as common, and the remaining is f of x, x plus h, f of x plus 2h, and so on, f of x plus nh, which can be written in the series form. And if we take limit n tends to infinity, this thing becomes integral from a to b f of x dx. This is we already know in classical calculus. You can see that this expression is very much similar to this expression with the only difference of negative sign. So this is equal to this one, this will be equal to some integral. So here we see that our h is x minus a over n. So we need to figure out which are our limits and how we can figure out the integral. If you can see, f of x plus jh is turned to f of x, and this can be done if you replace x by x minus jh. X minus jh, this cancels x minus jh, so it's only x. So we need to apply same technique here. So here h is x minus a minus 0 over n, and this becomes integral. This is my a and this thing is b, so b minus a, so integral from a to b, so a is 0, b is x minus a, and this is f of x minus, since x is in the limit, so it is not a variable here, so we take some other variable, say it t, and h, which is the height width of each rectangle, it represents dt. So this thing turns out to be this thing. So further, if I substitute x minus t equals u, and remember x is not variable with respect to this integration since it is involving t, so if I differentiate by t, this becomes minus dt equal to du, and if I change this thing, when t is 0, u becomes x, and when t is x minus a, which is x minus x plus a, x cancels, so it is a, and f of x minus t is u, and dt is minus du. We can switch the limits to adjust this negative sign, so this becomes integral a to x f of u du. This is my integral of first order. This is very simple. We can solve this very easily. So this is when alpha is 1. Now we see that what happens if we take alpha is equal to 2. Okay, so when alpha is 1, we established this result, and when alpha is 2, just if replace alpha by 2, so we get this result. Here gamma 2 plus j, we can use again the definition of gamma function, gamma n equal n minus 1 factorial. If we have 2 plus j, it becomes j plus 1, one less of this one, j plus 1 factorial, and by factorial function it becomes j plus 1 into j factorial. So this is j plus 1 into j factorial, and j factorial cancel out this factor, and gamma of 2 is 1 factorial again by this definition, which is 1. So this factor is just j plus 1. So this becomes limit n tends to infinity h square summation j0 to n 1 plus j or j plus 1 into f of x minus jh. This is what I left with. Okay, now if I in this under summation sign replace j to j minus 1, I'm just making one index before. This makes limit n tends to infinity h square, and now when j replace to j minus 1, so j minus 1 equal to 0, it means j is starting from 1. Since here if I replace j by j minus 1 and put 1 on the other side, so it's j1, and here since this j is equal to n, when I replace j by j minus 1, it becomes n plus 1, and this becomes j and f of x minus and j minus 1 into h, and then simplifies to limit n tends to infinity h square summation j1 to n plus 1 j of f of x minus j, and j is multiplied by h, so it's jh, and minus minus plus 1h, so it becomes x plus h minus jh. And if I replace x plus h equals some variable y, this becomes limit n tends to infinity h square summation j from 1 to n plus 1 j of f of y minus jh. This is h square outside. I put j 1h here and 1h here, so this adjust here, and now again using the Riemann integration, this is my f of y minus u, or you can take any number x into dt, and this again hg gh same thing, so it is t, so this becomes integral the same using the same definition 0 to x minus a t time f of x minus t dt, which again if we replace x minus t to u, this becomes, I write here, this becomes, if I again using x minus t equal to u and minus dt is equal to du, and when t goes to 0 u goes to x, and when t goes to upper limit x minus a, u goes to x minus a, x cancel a, and this becomes limit x to a t we can find here, which is x minus u f of x minus t, which is u, so f of u, and dt, which is minus u, so minus du, and we can adjust negative sign by replacing the integral, so this becomes limit a to x minus u f of u du. Very nice form. And now we have a pattern. According to pattern, if we put alpha 3, it becomes, okay, when alpha is 3, this becomes I cube f 1 over 2 factorial a to x minus u square f of u du. You can see the pattern, I square x minus u power 1, here it is cube, and now power 2, and from where it came, when alpha is 3, this is gamma of 3, which is 2 factorial, so it's 2 factorial. When alpha is 4, this becomes gamma of 4, which is 3 factorial, x minus u to the power cube, and f of u, so on. So it's a pattern, so can continue to nth form, so alpha is n, this becomes n of f 1 over n minus 1 factorial integral a to x minus u to the power n minus 1 f of u du, and here is an integer, and now we can change n to any arbitrary number alpha, so it becomes I alpha of f 1 over alpha minus 1 factorial, which can be again written as gamma function notation. This gamma of alpha integral a to x minus u to the power alpha minus 1 f of u du, and this is the very good definition of fractional integral of arbitrary order. Here, since we have a and x, and when we started this definition we saw that a was less than x, so here a is less than x, and because this depends on these limits, we also put these base points here, a and x. These are the base points. So this is called Riemann Liouville Fractional Integral, which is very good form, and we can apply this to any elementary functions. And if we have alpha and we have a is greater than x, in case a is not less than x is greater than x, we would just need to change the limits x to a in that case. So this is very good definitions. So in this lecture we have arrived at this result, Riemann Liouville fractional integral. In the next class we will see some basic properties of this fractional integral. Thank you for watching.